So good afternoon, everyone. I'm Francesco Collini, and today I will be introducing you to a joint project I carried out in the last 6 months in collaboration with the University of Leuven, where we investigated the possibility of assessing the fatigue limit of lattice structures using fracture mechanics. Here you can see the agenda of my presentation. I will start with a brief introduction with the focus, with the goal of motivating why so much engineering interest in lattice structures, and to contextualize the fatigue problem for lattice structures. So starting with the introduction, as you probably already all know, lattice structures are obtained by the periodic repetition in space of a unit cell. And I believe that we can appreciate how useful lattice structures could be in engineering by analyzing their material properties at the apparent macroscopic scale in an Ashby material selection diagram, where on the x-axis we have the density of the material, and on the y-axis you have the Young's modulus of the material. Sorry. Now we can see in the material selection diagram composites, metals, and human bones, and we can see that with the very simple equations proposed by Ashby, we can lattice structures allow to fill a portion of the diagram that is otherwise empty, and to obtain stiffnesses very similar to those of the human bones, and to fill a portion of the diagram that is characterized by stiffness to weight ratios that are very high, and thus suitable for producing lightweight structures. So we are probably wondering why we don't see lattice structures used across the entire industry, but limited to academia. And one of the leading causes is fatigue. To understand why fatigue is such a mess for lattice structures, I propose you this very simple case study where we have a generic lattice structure subjected to a remote tension loading, which is the simplest scenario we can probably imagine. And if we look closer at the lattice structure at the scale of individual unit cells, we can see that there are a lot of stress concentrations, which can potentially be very severe at each node of the lattice structure. And if we look even closer, we can see that there are defects at these stress concentrations, further weakening the structure fatigue limit. So we can understand that in order to have a fatigue limit estimation model that is robust to changes of the structure, of the actual lattice structure geometry, and to the remote loading conditions, we need to be able to estimate the fatigue limit starting from the base material properties and obtaining that of the lattice structure. And that will be exactly the aim of my presentation. How to do it? Let's move on with the theoretical background. And let's start by considering a defective cylindrical specimen, where we can see here the defect, subjected to a remote fatigue loading with a range delta sigma g. We can analyze the relationship between the crack size or defect size and the fatigue limit in an Lazzari Meneghetti model diagram, where on the x-axis we have the effective size of the defect, and on the y-axis we have the fatigue limit of the defective material. And we can identify 3 different trends. The first one for small defects or short cracks, where the fatigue limit approaches that of the defect-free material. The linear elastic portion of the diagram, where the defect or the crack behaves like a short crack. And if we have very large defects with a rounded geometry, we can reach the full notch sensitivity region, which is included in the Lazzari Meneghetti diagram, but is not relevant for this presentation, and so it will be removed. What happens? Experimental data will follow a smoother trend that is well described by the Lazzari Meneghetti model, and here you can see the reference for this diagram. What happens when we have a sharply notched material? Is it possible to obtain a similar relationship like that for defective cylindrical specimens? The answer is yes. The professors Azzori, Lazzarini, and Meneghetti proposed another Lazzarini Meneghetti diagram, sorry for the repetition, for sharply notched specimens. It is formally identical, as we can see here, with the only difference being the flatter portion for the singularity that is related to a lower singularity exponent for the stress field for a sharp notch. So with this diagram, we are now able to estimate the fatigue limit of defective materials and sharply notched materials. And we can now move on to the validation of the diagram, starting from the materials and methods, and in particular from the specimen manufacturing. We analyzed lattice structures with a unit cell that is named star or BCC, and you can see it here. The unit cell size is 2 millimeters, and the strut diameter is 0.5 millimeters, the nominal one. The lattice the specimens are characterized by 3 different regions: a bulk regions, a bulk region, sorry, where the sample will be clamped to the testing system. Then we have a density gradient before reaching the constant density gradient, the constant density region, which is the one that I'm going to test. But we need the density gradient in order to avoid having the fatigue failure at this interface between the bulk part and the constant density part. The material used is an A205 alloy in stress relief conditions, heat treated to obtain stress relief at 270 degrees for 2 hours, followed by furnace cooling. And for the sake of completeness, I'm reporting here the chemical composition of the alloy because it's not that well known, and the quasi-static mechanical properties for the as-built material and the stress relief material. The Lattice samples were built using 2 different sets of process parameters that were developed by my colleagues at TU Leuven. So for the bulk portion, that is from the top to the end of the density gradient, where the lattice structure is quite thick, we use the more conventional scanning strategy where we do an contour scanning pass, followed by the zigzag in-field scanning with kind of high laser power at density. And for the portion characterized by thin struts, we used a completely different scanning strategy that is characterized, as you can see here, by multiple contour scanning passes instead of the zigzag you can see on the left. And also the laser powers are much lower when compared to the bulk part. So moving on to the experimental fatigue analysis, tests were performed under remote tension, so a very simple loading conditions. Here you can see the static scheme of the test I'm conducting, which is again very simple due to the simplicity of the loading condition in testing. And here you can see the SN data obtained experimentally, the preliminary one. I'm still carrying some more tests, where on the x-axis, we have the number of cycles to failure. On the y-axis, we have the range of the homogenized nominal stresses that are computed as using this equation. And to understand the meaning of the markers, these circle markers means that this test reached the run-out conditions, and I retested it with this black at a higher stress level, and it failed here. While these crosses are all related to fatigue-failed specimens at the first load level. By analyzing the fracture surface, which is in the middle of the sample, not exactly here, I forgot to take a picture, but it's outside of the density gradient region. And if we look at the fracture surface closer, we can recognize this characteristic pattern where we have multiple crack initiations at each of the corners of the node. And we can see that there are quite small defects. They are very rare and small, and that's kudos to my colleagues at TU Leuven who developed the scanning, the printing parameters quite well, I would say. And it's very interesting to know that we have multiple, again, crack initiation with multiple crack planes initiating from each of the corners. And that is suggesting that probably it's behaving like a cut notch rather than an effective material. Again, I'm plotting now the fracture surface of this specimen. Again, here you can see the cross section, the zoom in for this node, and we can recognize the same exact pattern. We have a rather bigger node, pore here, but again, we have initiation from this corner and this corner, regardless of the presence of the defect. So as a result, even if present, and I want to highlight rare, defects do not trigger the fatigue crack initiation, and this suggests that the behavior is that of a shut notch. Now we can use the Adversarial Meneghetti diagram calibrated for a sharp notch. And here you can see the Adversarial Meneghetti diagram calibrated for the base materials properties that were estimated. So delta sigma 0, 155 megapascals, estimated from the static strength of the base material, and the not stress intensity factor in threshold range of 2.55 megapascal. And pay attention to this singularity exponent, which was estimated from the delta KT-HLC that was measured in lab during this experimental analysis. Now we have to estimate the effective crack size to have an estimate of the fatigue limit. To do so, I simulated a portion of the lattice structure, as you can see here, and I used the peak stress method, which is a finite element oriented procedure to rapidly estimate the not stress intensity factor, from which I can then estimate the effective crack size. So looking at the model I used, here is a portion of the finite element model for the sake of saving some space. I simulated only a portion of the models, taking advantage of all the symmetries of the model. And there is a remote load delta sigma g. Here you can see, a cross section of the specimen. And the elements I used for the simulation are tetrahedrons with 10 nodes. The element size is a fifth of the strut diameter, that is 0.1 millimeter, which is quite coarse to obtain a characteristic of the singularity. And the solver is ANSYS mechanical. By performing the simulation, I can see that the most critical points are the corners for each node, independently of the fact that they are in the middle of the sample or in the outside of the sample. So we can predict initiation from this node, this. So every one of the point where there are the crosses, but also the others. Using this procedure, I estimated a crack size of about 20 centimeters, which is quite high, but it makes sense because the struts are very, very small. And if I compare this prediction with experimental results, I obtain this, let's say, this estimate of the fatigue limit, which is in good agreement with the experimental results I obtained. I kept the scatter band of the peak stress method for the estimation of the effective crack size. However, I'm quite satisfied with the prediction. We are quite satisfied with the prediction because the exact estimates is really close to the endurance limit at about 10 million cycles, so in the very high cycle regime. Moving on to the conclusions, we saw that lattice structures are suitable for producing lightweight materials, that a fatigue criterion for lattice structures must account for the local stress concentrations and the presence of defects simultaneously. Using the multi-contour scanning strategy developed by my colleagues at TU Leuven, we obtain an almost defect-free lattice structures. And the Celik Meneghetti model offers an accurate material property to structure property relationship for the fatigue limit prediction. Furthermore, taking advantage of the peak stress method, this estimate is quite fast. Moving on to the future developments, I'm already testing more complex unit cells than the BCC I've shown you today, in particularly the diamond and the diamond adaptive that was developed at TU Leuven. And for these kind of unit cells, I will have to take into account the potential presence of multi-axiality, and I will have to perform a more detailed analysis of the sensitivity of the result based on the simulated geometry. With this, I conclude my presentation. I thank you for your kind attention.